हेलो फ्रेंड्स, तो राना अकेडमी में आपका स्वागत है। हमने स्टार्ट किया 12th क्लास की एनसीईआरटी को वन शॉट सीरीज, जिसमें हमने 8th यूनिट तक कंप्लीट किया है। तो स्टार्ट करते हैं 9th यूनिट, कोऑर्डिनेशन कंपाउंड्स। In the previous unit, we learned that the transition metals form a large number of complex compounds in which the metal atoms are bound to a number of anions or neutral molecules by sharing of electrons. In modern terminology, such compounds are called coordination compounds. The chemistry of coordination compounds is an important and challenging area of modern inorganic chemistry. New concepts of chemical bonding and molecular structure have provided insights into the functioning of these compounds as vital components of biological systems. Chlorophyll, hemoglobin, and vitamin B12 are co-coordination compounds of magnesium, iron, and cobalt, respectively. Variety of metallurgical processes, industrial catalysts, and analytical reagents involve the use of coordination compounds. Coordination compounds also find many applications in electroplanting, textile dyeing, and medical chemistry. Werner's theory of coordination compounds. Alfred Werner, 1866 to 1919, and a Swiss chemist, was the first to formulate his ideas about the structures of coordination compounds. He prepared and characterized a large number of coordination compounds and studied their physical and chemical behavior by simple experimental techniques. Now, Werner proposed the concept of primary valence and secondary valence for metal ion binary compounds such as CrCl3, COCl2, and PdCl2 have primary valence of 3 to 2 and 2 respectively. In a series of compounds of cobalt chloride with ammonia, it was found that some of the chloride ions could be precipitated as AgCl on adding excess silver nitrate solution in cold, but some remained in solution. 1 mole COCl2 .6 NH3 LO gave 3 mole AgCl. These observations, together with the results of conductivity measurements in solution, can be explained if six groups in all, either chloride ions and ammonia molecules or both, remain bonded to the cobalt ion during the reaction. The compounds are formulated as shown in table 9.1, where the atoms within the square brackets form a single entity which does not dissociate under the reaction conditions. Werner proposed the term secondary valence for the number of groups bound directly to the metal ion. In each of these examples, the secondary valence are with 6 formulation of cobalt. Table 9.1, formulation of cobalt chloride ammonia complexes. Note that the last two compounds in table 9.1 have identical empirical formula COCl3 dot 4 times NH3 but distinct properties. Such compounds are termed as isomers. Werner in 1898 propounded his theory of coordination compounds. The main postulates are the coordination compounds metals show two types of linkages, valences, primary and secondary. Primary valences are normally ionizable and are satisfied by negative ions. The secondary valences are non-ionizable. These are satisfied by neutral valence molecules or negative ions. The secondary valence is equal to the coordination number and is fixed for a metal. The ions groups bound by the secondary linkages to the metal have characteristic partial spatial arrangement corresponding to direct coordination numbers. In modern formulations, such special arrangements are called coordination polyhedra. The spaces within the square bracket are coordination entities or complexes, and the ions outside the square bracket are called counterions. He further postulated that octahedral, tetrahedral, and square planar geometrical shapes are more common in coordination compounds of transition metals. Thus, CONH3 6 times the tri-negative, COCl3 COClNH3 5 times the positive plus, and COCl2 NH3 4 times the positive are octahedral entities, while NiCO4 and PTCl4 negative are tetrahedral and square planar respectively. Difference between the double salt and the complex. Both double salts as well as complexes are formed by the combination of two or more stable compounds in stoichiometric ratio. However, they differ in the fact that double salts such as carnallite, KCl, MgCl2.6 times H2O, more salt FeSO4 dot NH4 2 times SO4 6 times H2O, potash alum KAl SO4 2 times 12 times H2O, etc. dissociate into simple and completely without water. However, complex ions such as Fe Efficient 6 times negative of K4 efficient 6 times do not dissociate into Fe positive and Cn negative ions. Definition of some important terms determining pertaining to coordination compounds. Coordination entity. The coordination entity constitutes a central metal atom or ion bonded to a fixed number of ions and molecules. For example, COCl3 and H3 3 times. There is a coordination entity in which the cobalt ion is surrounded by 3 ammonia molecules and 3 chloride ions. Other examples of NiCO4 times, PTCl2 3 NH3 2 times, FeCN 6 times tetranegative, CONH3 6 times positive, central atom or ion in a coordination entity. The atom or ion when a fixed number of ions groups are bound in a definite geometrical arrangement around it is called a central atom or ion. For example, the central atom ion in the coordination entities NiCl2 CH2O 4 times, COClNH3 3 times positive, and FeCN 6 times positive, and Ni positive, CO3 positive, and Fe positive respectively. These central atoms ions are also referred to as Lewis acids. Ligands. The ions or molecules bound to the central atom or ion in the coordination entity are called ligands, and these may be simple ions such as Cl negative, small molecules such as H2O and NH3, larger molecules such as H2 and CH2, CH2 and H2. Ni, CH2, CH2, NH2 3 times, or even macromolecules such as proteins. When a ligand is bound to a metal ion through a single donor atom, as with Cl negative H2 and NH3, the ligand is said to be unidentate. When a ligand can bind through two donor atoms, as in ligands, it's said to be didentate. And when several donor atoms are present in a single ligand, as in NiCH2, CH2 NH3 3 times, the ligand is said to be polydentate. Ethylene diaminate tetraacetate ion is an important hexadentate ligand. It can bind through 2 nitrogen and 4 oxygen atoms to a central metal ion. When a diode polydentate ligand uses its 2 or more donor atoms simultaneously to bind a single metal ion, it is said to be identicity of a ligand. Such complexes called chelate complexes. Identicity of the ligand. Such complexes called chelate complexes tend to be more stable than similar complexes containing undented ligands. A ligand which has two different donor atoms and either the of the two ligands in the complex is called ambidentate ligand. Examples of such ligands are the NO2 negative and CN negative ions. NO2 negative ion can incorporate either through nitrogen or through oxygen to a central metal atom or ion. Similarly, SCN negative ion can coordinate through the sulfur or nitrogen atom. Coordination number. The coordination number Cn of the metal ion in a complex can be defined as the number of ligand donor atoms to which the metal is directly bonded. For example, in the complex ions PtCl6 negative and the NiCNH3 trying 4 times the positive. The coordination number of Pt and Ni are 6 and 4 respectively. Similarly, in the complex ions FeCO2 C2O4 3 times strand negative and COEN 3 times strand positive. The coordination number of both Fe and CO is 6 because C2O4 negative and En ethane 1 to diamine are didentate ligands. Coordination sphere. The central atom ion and the ligands attached to it are enclosed in square bracket and is collectively termed as the coordination sphere. The ionization and the groups are written outside the bracket and are called counter ions. For example, in the complex K4 efficient system, the coordination sphere is efficient systems negative and the counter ion is K positive. Coordination polyhedron and the spatial arrangement of the ligand atoms which are directly attached to the central atom ion defines the coordination polyhedron about the central atom. The most common coordination polyhedra are octahedral, square planar, and tetrahedral. For example, CONH3 6 times tripositive is octahedral, NiCO 4 times is tetrahedral, and PtCl 4 times dinegative is square planar. Figure 9.1 shows the shapes of different coordination polyhedron. Figure 9.1 shapes of different coordination polyhedra. M represents the central atom and the L indicate unidentate ligand. Oxidation number of central atom. The oxidation number of the central atom in a complex is defined as the charge it would carry it all. Now the ligands are removed along with the election of pairs and that are shared with the central atom. The oxidation number represented by a Roman numbered in parentheses following the name of the coordination entity. For example, co-oxidation number of copper in CuCN 4 times tripo negative is +1 and it is written in Cu. Now homoleptic and homoleptic and heteroleptic complexes in which a metal is bound to only one kind of donor, complexes in which a metal is bound to only one kind of donor groups. Example, CuNH 4 times tripositive are known as homoleptic complexes in which the metal is bonded to more than one kind of donor groups. CONH3 4 times Cl2 and positive are known as heteroleptic. Nomenclature of coordination compounds. Nomenclature is important in coordination chemistry because of the need to have an unambiguous method of describing formulas and writing systematic names, particularly when dealing with isomers. And the formulas and names are adapted for coordination entities are based on the recommendations of the International Union of Pure and Applied Chemistry. Formulas of mononuclear coordination entities. The formula of a compound is a shorthand tool used to provide base information about the constitution of the compound in a concise and convenient manner. Mononuclear coordination entities contain a single central metal atom. The following rules are applied while writing the formulas. The central atom is listed first. The ligands are then listed in alphabetical order. The placement of a ligand in a list does not depend on its charge Polydentate ligands are also listed alphabetically. In case of abbreviated ligands, the first letter of the abbreviation is used to determine the position of the ligand in a alphabetical order. The formula for the entire coordination entity, whether charged or not, is included in square brackets. When ligands are polyatomic and their more formulas are included in parentheses, ligand abbreviations are also included in parentheses. There should be no space between the ligands and the metal within the coordination sphere. When the formula of a charged coordination entity is to be written without that of the counterion, the charge is indicated outside the square brackets as the right superscript with the number of before the sign. For example, CN6 try negative, CRH2O6 times try positive, etc. The charge of the cation is balanced by the charge of the anion. Naming of mononuclear coordination compounds. The names of coordination compounds are derived by following the principles of additive nomenclature. Thus, the groups that surround the central atom must be identified in the same. They are listed as prefixes to the name of the central atom along with any appropriate multipliers. The following rules are used when naming coordination compounds. The cation is named first in both positively and negatively charged coordination entities. The ligands then and are named in an alphabetical order before the names of the central atom. This procedure is reversed from writing formula names of the anionic ligands and in O, those are of neutral and cationic for CO and nitrosyl for NO. While writing the formula of coordination entity, these are enclosed in brackets. Prefixes mono, di, tri, etc. are used to indicate a number of the individual ligands in a coordination entity. When the names of the ligands includes the numerical prefix, then the terms bis, tris, parenthesis, for example NiCl2 pH3 two times is named as dichloride bis, triphenyl phosphoine nickel. Oxidation state of the metal in cation, anion and neutral coordination entity is indicated by Roman numeral and parenthesis. If the complex ion is cation, the metal is named as same as the element. For example, CO in a complex cation is called cobalt and PT is called platinum. If the complex ion is an anion, the name of the metal ends with the suffix etc. For example, CO in a complex anion, COSCN 4 times negative is called as cobaltate. For example, CO in a complex anion, COSCN 4 times negative is called cobaltate. For some metals, the Latin names are used in the complex anions. The ferrite ion for ferrous. Isomerism in coordination compounds, geometrical isomerism, optical isomerism, stereoisomerism. First is geometrical isomerism, second is optical isomerism, structural isomerism, first linkage isomerism, second is coordination isomerism, third is ionization isomerism, fourth is solvent isomerism. Linkage isomerism, coordination isomerism, ionization isomerism, solvent isomerism. Bonding and coordination compounds, valence bond theory. Magnetic properties of coordination compounds. Limitations of valence bond theory. Crystal field theory. Color in coordination compounds. Limitations of crystal field theory. Bonding in metal carbonyls. Importance and applications of coordination compounds. Coordination compound की summary. The chemistry of coordination compounds is an important and challenging area of modern inorganic chemistry. During the last 50 years, the advances in this area have provided development of new concepts and models of bonding and molecular structure. Novel breakthrough in chemical industry and vital insights into the functioning of critical components of biological systems. The first systematic attempt at explaining the formation, reactions, structure, and bonding of a coordination compound was made by A. Werner. His theory postulated the use of two types of linkages, primary and secondary, by metal atom ion in the coordination compound. In the modern language of chemistry, these linkages are recognized as ionizable, ionic and non-ionizable covalent bonds, respectively, using the property of ionization isomerism. Werner predicted the geometrical shapes of the large number of coordination entities. The valence bond theory (VBT) explains with reasonable success the formation, magnetic behavior, and geometrical shapes of coordination compounds. It, however, fails to provide the quantitative interpretation of magnetic behavior and has nothing to say about the optical properties of these compounds. The crystal field theory CFT, to coordination compounds, is based on the effect of different crystal fields provided by the ligands taken as point charges on the degeneracy of d orbital energies of the central metal atom ion. The splitting of the d orbital provides different electronic arrangements and strong and weak crystal fields. The treatment provides for quantitative estimations of orbital separation energies, magnetic moments, and spectral and stability parameters. However, the assumption that ligands constitute the point charges creates many theoretical difficulties, and the metal carbon bond in metal carbonaceous processes possesses both sigma and pi character. The ligand to metal is sigma bond, and metal to ligand is pi bond. This unique synergic bonding provides stability to metal carbonaceous carbonaceous coordination compounds are of great importance. These compounds provide critical insights into the functioning of and structure of vital components of biological systems. Coordination compounds also find extensive applications in metallurgical processes, analytical and medicinal chemistry. सो कोऑर्डिनेशन कंपाउंड 12th का केमिस्ट्री का एनसीईआरटी का हमारा वन शॉट सीरीज स्टार्ट किया है हमने। तो कोऑर्डिनेशन कंपाउंड हमने यहाँ पर ख़त्म किया है, जो कि बहुत ज़्यादा शॉर्ट में कवर अप किया है हमने वो सभी पॉइंट्स को। वर्नर्स थ्योरी ऑफ कोऑर्डिनेशन कंपाउंड्स फर्स्ट हमने देखा, उसके बाद हमने फॉर्मुलेशन ऑफ कोबाल्ट क्रोमाइड क्लोराइड अमोनियम कॉम्प्लेक्सेस देखा टेबल में। उसके बाद हमने देखा डेफिनेशंस ऑफ सम इम्पॉर्टेंट टर्म्स पर्टेनिंग एंड कोऑर्डिनेशन कंपाउंड्स, nomenclature of coordination compounds, formulas, mononuclear coordination entities, naming of mononuclear coordination compounds. then उसके बाद हमने देखा आइसोमेरिज्म इन कोऑर्डिनेशन कंपाउंड्स, जियोमेट्रिकल आइसोमेरिज्म, ऑप्टिकल आइसोमेरिज्म, स्टीरियो आइसोमेरिज्म में, और स्ट्रक्चरल आइसोमेरिज्म में, लिंकेज आइसोमेरिज्म, जो कोऑर्डिनेशन आइसोमेरिज्म, आयनाइजेशन आइसोमेरिज्म, सॉल्वेट आइसोमेरिज्म, bonding and coordination compounds, valence bond theory (VBT), magnetic properties of coordination compounds, limitations of valence bond theory, crystal field theory (CFT), color of coordination compounds, limitations of crystal field theory, bonding and metal carbonaceous, importance of and application coordination compounds, then summary. सो यहाँ पर कोऑर्डिनेशन कंपाउंड को वन शॉट सीरीज वन शॉट में कवर अप किया है हमने कोऑर्डिनेशन कंपाउंड्स को। सो यहाँ पर ख़त्म होता है कोऑर्डिनेशन कंपाउंड, जो कि हमारा 9th यूनिट 12th क्लास की केमिस्ट्री का। सो प्लीज़ लाइक शेयर एंड सब्सक्राइब। थैंक यू सो मच फॉर वॉचिंग।